welcome to the deep dive.
Mhm.
Today, we're pulling back the curtain on the digital world.
Getting into the nuts and bolts.
Exactly. To understand the very backbone of how our apps, our websites, well, how they actually work. We're talking about system design.
Yeah.
Our mission today is pretty straightforward. We want to take you from, the fundamental building blocks of the internet
The basics.
right through to the really sophisticated architectures that power everything. Your streaming service, that quick Google search you just did,
Mm-hmm.
this is basically your shortcut to really understanding the digital world around you, not just, like, using it.
And that understanding is, I think, really crucial. System design isn't just for the software engineers coding this stuff.
Right.
It's about grasping how information flows, what makes a system robust when millions of people are hitting it at once,
Yes, scalability.
and why your favorite app feels so snappy and responsive. It's recognizing this intricate dance of components that underpin, well, modern life, really.
So, okay, you type google.com into your browser, hit enter, and poof, there it is. But what really happens in that split second?
Mm-hmm. Chuckles. It's a lot.
We're going to trace that journey today. Uncover the secret languages these services speak.
APIs and things.
Yeah, explore how all the world's data gets organized, stored,
SQL, no sequel.
and find out what makes these systems unbelievably fast and scalable. Get ready to connect some serious dots, I think.
Sounds good.
Okay, let's start with the absolute bedrock, the foundation of how pretty much anything works online.
Mm-hmm.
The client-server model.
Right.
We've all used it, probably without even thinking about it.
Yeah.
Your phone is the client, right? And Facebook's backend, that's a server.
Exactly. It's that fundamental split. You have devices asking for services
Clients.
and powerful machines providing them servers. That's the core idea. When we say client, we mean your web browser, your mobile app, maybe even your smart fridge these days.
Wow.
It's what you directly interact with.
Yeah.
It handles the user interface. It kicks off the requests. It's the requester.
And the server.
The server is the workhorse. It's a specialized computer or maybe just a program designed to just sit there and listen for those requests.
Okay.
And when one comes in, it processes, it maybe fetches data, runs calculations, whatever it needs to do, and then sends a response back to that client.
And the beauty is, it sounds simple, but the scale can be just immense, right?
Oh, absolutely.
Your client sends a request over the network, the server gets it, does its thing, sends a response back.
Yep.
And that interaction happening billions, maybe trillions of times a second globally,
Yeah.
that's the engine driving the whole internet. Every message, stream, click it, starts right there.
That's the dance.
So let's go back to that google.com example.
Hmm.
It feels instant, but you said there's a whole symphony playing out. Where does that journey actually begin?
Right, it's not magic. The very first step before your browser even talks to a Google server is something called a DNS lookup.
DNS, domain name system.
Exactly. Your browser knows google.com. That's easy for us humans. But computers need numbers, an IP address.
Like a phone number for the server.
Precisely. So the browser queries the DNS, which is like the internet's massive distributed phone book. It translates google.com into an IP address, maybe something like 142.250.191.46.
Okay, so now it has the number to call.
Now it has the number. The next step is establishing a reliable connection using PCP, Transmission Control Protocol.
TCP, right.
Think of it like a quick check-in before a serious conversation. Your browser sends a SYN packet. Hello, you there?
SYN.
The server replies with SYN ACK. Yep, I'm here, ready. You ready?
SYN ACK.
And your browser sends back an ACK. Yep, ready.
Or CK, the three-way handshake.
That's the one. It makes sure both sides are ready and synchronized so data doesn't get dropped before the real message even starts.
Got it. Connection established. Then what?
Then your browser sends the actual HTTP request, or, more likely for Google, HTTPS, which means it's secure, encrypted.
Okay.
This request is literally asking the server, hey, can I have the resources for the Google homepage?
And the server.
The server gets that request,
Right.
figures out what's needed, the HTML for the structure, the CSS for the styling, the JavaScript for, interactivity.
Making things happen on the page.
Right. It gathers all that stuff, bundles it into an HTTP response, and sends it back.
And finally, my browser gets it.
Finally, your browser receives that response and starts rendering the page, drawing it on your screen. And it might even make more requests as it goes for images or other assets needed to finish the job.
Wow. Okay, that's way more involved than just type and click.
It really is a rapid-fire series of exchanges.
You mentioned the browser asks the server for things with HTTP.
Yeah.
Is there like a standard language for those asks?
Absolutely. HTTP defines a set of standard verbs or methods that tell the server what action the client wants to perform.
Verbs, like action word.
Exactly. When you just fetch a web page like loading Google, your browser sends a GET-T request. Get me this page.
Simple enough.
If you're submitting a form, like signing up for something or posting a comment, that's usually a POST request. You're sending new data to the server.
Okay, defetches, post descends, new stuff.
Then there's PUT, which is typically used to completely update an existing resource, like replacing your profile information entirely.
Replace, okay.
And delete is, well, pretty self-explanatory. It tells the server to remove a specific resource.
Got it. Get, post, put, delete. Those are the main ones.
Those are the big four. They form the core vocabulary for how clients and servers interact over HTTP. Now think about this. Once that initial request hits a server, that server often needs help. It might need data from another specialized service or need to tell another system to do something.
So servers talk to other servers.
All the time. And that communication is governed by APIs, application programming interfaces.
APIs. Heard that term a million times.
They're basically the set of rules, the contract, that defines how different software components should interact, how Service A asks Service B for information, and what Service B promises to send back.
Okay, so APIs are the contracts between services. And I keep hearing about two main styles or types of these contracts, REST and GraphQL. What's the deal there?
Yeah, that's a really important distinction in modern system design. They represent different philosophies. REST, which stands for Representational State Transfer, is maybe the more traditional style you see.
Okay.
With REST, you interact with distinct resources through specific URLs or endpoints. Like you might have users to get a list of users or products123 to get details for a specific product.
Makes sense, like addresses for data.
Exactly. And the server usually decides the structure of the data you get back for each endpoint. The challenge sometimes is you might get more data than you need for a particular screen.
That's the overfetching you mentioned.
Right. Or you might have to make multiple requests to different endpoints to gather all the pieces of data you actually need for one view.
Underfetching? Okay.
REST is great for many things, especially simpling resource-focused APIs where the data needs are pretty stable and well-defined.
So what about GraphQL then? How does it differ?
GraphQL came along, developed by Facebook initially, specifically to address those overfetching and underfetching problems. It's actually a query language for your API.
A query language? Like SQL for databases?
Kind of, yeah. Instead of multiple endpoints, GraphQL typically exposes just one endpoint, and the client sends a query specifying exactly the data fields it needs.
So the client is in charge of what it gets back.
Precisely. The client dictates the exact shape of the response. Imagine you need the user's name from the user resource and just the titles of their last 3 blog posts from the post resource. With GraphQL, you can ask for exactly that in a single request and get just that back.
No extra fluff, no need for 5 different calls.
Exactly. It solves over-underfetching beautifully. This makes it super powerful for complex applications, especially mobile apps, where network efficiency is critical or when your data needs are constantly evolving.
That's a really clear difference. Client dictates versus server dictates the response shape.
That's a good way to put it.
Okay, so services are talking, data's flying around via APIs, maybe REST, maybe GraphQL. But where does all this information actually live? Where is it stored? This feels like a huge decision.
It's absolutely one of the most critical decisions in system design. And you're right, there's often this fundamental divide people talk about, SQL versus NoSQL databases.
Right, the 2 big categories. What's the core difference?
It really boils down to their data model and schema flexibility. SQL databases, often called relational databases, think MySQL, PostgreSQL, store data in highly structured tables.
Rows and columns, like a spreadsheet.
Exactly, with predefined columns, data types, and strict relationships defined between tables. They use a schema-on-write approach.
Meaning you have to define the structure before you put any data in.
Precisely. The schema is rigid and enforced by the database itself. Now, NoSQL databases, which means not only SQL really are different, they offer much more flexible data models.
Like what?
Well, you have key-value stores like Redis, document databases like MongoDB, where data is stored in JSON-like documents, column family stores like Cassandra, even graph databases like Neo4j. The models vary wildly.
So much less rigid.
Much less. They typically use a schema-on-read approach. The structure isn't enforced when you write the data. It's more flexible, defined when you actually read or query the data. This allows for faster iteration and handling varied data types.
That flexibility sounds appealing. What about handling massive amounts of data, like scaling?
That's another key difference. Traditionally, SQL databases scale vertically, meaning to handle more load, you make the single server bigger, more CPU, more RAM, faster disks.
Scaling up.
Scaling up. NoSQL databases, on the other hand, were often designed from the ground up to scale horizontally.
Scaling out.
Right. You add more servers to distribute the data and the load across a cluster of machines. This is generally much more cost-effective and practical for handling truly web-scale data volumes.
Okay, so structure versus flexibility, vertical versus horizontal scaling. What about data reliability? I hear terms like ACID.
Ah, yes, consistency. SQL databases typically provide strong ACD guarantees. That stands for atomicity, consistency, isolation, durability.
Sounds solid.
It is. It ensures transactions are reliable, either the whole thing completes successfully or none of it does. Essential for things like financial systems, banking, e-commerce checkouts. You can't have mistakes there.
Definitely not. How does NoSQL handle that?
NoSQL databases often make a trade-off. They tend to prioritize availability, the system is always responsive, and partition tolerance, it keeps working even if parts of the network fail, over strong consistency. They often offer what's called eventual consistency.
Eventual consistency, meaning
Meaning if you write data, it might take a short amount of time for that change to propagate to all the replicas or nodes. So for a brief moment, different users might see slightly different data, but eventually it will all become consistent.
okay, so maybe not ideal for my bank balance, but perhaps okay for my social media feed update.
Exactly, it's a trade-off. SQL for strong integrity needs. NoSQL often better for huge data sets, high-rate volumes, flexible data, where brief inconsistencies are acceptable. Think social media, IoT data, real-time analytics.
That makes the choice much clearer. It depends entirely on the requirements. Now, digging into databases a bit more, performance is always key. How do databases actually find the specific piece of data you ask for quickly without scanning like billions of rows?
Ah, the unsung hero. Indexes.
Indexes, like in the back of a book.
Precisely like that. A database index is a special lookup table or data structure that the data system can use to speed up data retrieval operations.
How does it work?
Instead of reading through every single row in a table to find the value you're looking for, a full table scan, which is super slow, the database can use the index, which is optimized for searching specific values, to directly locate the required rows much, much faster.
So it's like having a pre-sorted list pointing directly to the data.
Exactly. On commonly queried columns like user IDs, usernames, product SKUs indexes can dramatically improve performance. They do come with a cost. They take up storage space and can slightly slow down write operations because the index also needs to be updated. But for read-heavy workloads, they're absolutely essential.
Makes sense.
They're-
Okay, so indexes help the database itself work faster. But what if even that's not fast enough? Database access, especially from disk, is still relatively slow compared to, say, accessing memory.
You're hitting on a crucial point. That's where caching comes in.
Caching, storing things closer, faster.
Exactly. A cache is a high-speed data storage layer. Typically, it uses in-memory storage like RAM, which is orders of magnitude faster to access than disk-based databases.
Orders of magnitude, wow.
Oh yeah, we're talking microseconds versus milliseconds or even seconds. So the cache stores a subset of your data, usually the most frequently accessed data, where it can be retrieved almost instantly.
So why is this so important in system design?
Two main reasons. First, it dramatically reduces latency. Faster data access means a snappier, more responsive application for the user, better user experience.
Always good.
Second, it significantly reduces the load on your main database. If you can serve 90% of your read requests from the super fast cache, your database only has to handle the remaining 10%, plus the writes. This protects the database from getting overwhelmed and potentially falling over, especially during traffic spikes.
Okay, faster for users, less stress on the database. Win-win. How does the application know what to put in the cache and when? What's a common way to manage this?
A very common and effective pattern is called cache aside, sometimes called lazy loading.
Cache aside, how does that work?
It's pretty straightforward. When your application needs a piece of data, one, it first checks the cache.
Look in the fast place first.
Right. If
Yeah.
the data is, we would call that a cache hit, great. It returns the data immediately, super fast.
Nice.
Two, if the data is not in the cache, a cache miss, then the application queries the database for the data.
Okay, go to the source of truth.
Exactly. Once it gets the data from the database, it does two things. Three, it stores a copy of that data in the cache for next time.
Sure.
And then it returns the data to the application and ultimately the user.
So it populates the cache only when data is actually needed and missed.
Precisely. It keeps frequently accessed data hot and fast in the cache, while the database remains the persistent, authoritative source. It's a really effective balance.
Got it. Okay, so we've assembled quite a few pieces now. Client server, networking, APIs, databases, indexing, caching. These are powerful tools. But how do we combine them to build systems that can handle, millions or billions of users?
Yeah.
Systems that are truly scalable and don't fall over.
Right, this is where we move into core distributed systems concepts. We're talking about managing multiple machines working together.
Okay.
And the first concept is scaling. We tick around it with databases, but it applies broadly. You have two main approaches.
Vertical and horizontal.
Exactly. Vertical scaling, or scaling up, means making a single server more powerful. More CPU, more RAM, faster storage, like upgrading your laptop.
Simple, but has limits.
It has limits, and it can get very expensive very quickly. There's only so big you can make one machine. The dominant approach for large-scale systems is horizontal scaling, or scaling out,
Adding more machines?
adding more servers to your pool. Instead of one super powerful server, you have dozens, hundreds, or even thousands of commodity servers working together. This is the foundation of most modern large-scale internet services.
But if you have hundreds of servers, how does the incoming traffic know which one to go to? You can't just give users a list of 100 IP addresses.
Chuckles. No, definitely not. That's where load balancers come in.
The traffic cops.
Good analogy. A load balancer sits in front of your pool of servers. It receives all incoming requests and intelligently distributes them across the available backend servers.
How does it decide where to send a request?
There are various algorithms. The simplest is round robin, just send requests to each server in turn. Server 1, server 2, server 3, back to 1.
Fairly distributing the load.
Yep. Others are more sophisticated, maybe checking server load or response time before deciding. But the goal is the same. Spread the work, prevent any single server from being overloaded, and improve overall availability. If one server fails, the load balancer just stops sending traffic to it.
Smart. What about speeding up the delivery of content itself, like images or videos, especially to users far away from the main servers?
That's the job of a content delivery network, or CDN.
CDNs, right.
CDNs are a globally distributed network of servers. They cache copies of your static assets, images, videos, CSS files, JavaScript files at locations called edge locations, which are physically closer to your end users.
So if I'm in London and the main server is in California, the image comes from a server near London.
Exactly. Instead of the request traveling all the way across the Atlantic and back, it gets served from a nearby CDN edge server. This dramatically reduces latency and improves load times, especially for users far from your origin servers. It also offloads a ton of traffic from your main application servers.
Makes total sense. Now, going back to databases for a second, we talked about horizontal scaling for NoSQL. How do you scale traditional SQL databases when one massive server isn't enough?
Good question. Scaling relational databases horizontally is trickier, but there are common patterns. One is using read replicas.
Read replicas.
Yeah. You have your main database server, the primary or master, that handles all the writes. Then you create one or more read-only copies, replicas, that synchronize with the primary. Your application can then direct all or most of its read queries to these replicas.
So you separate the reading load from the writing load.
Exactly. Since many applications have far more reads than writes, this can significantly boost performance and reduce load on the primary database.
Okay, that helps with read load. What if the data itself is just too massive to fit on one machine, even for writes?
Then you need to move to sharding, also known as partitioning.
Sharding. Sounds like breaking glass.
Oh, Chuckles, kind of. You're literally splitting your database into smaller, more manageable pieces called shards. Each shard contains a subset of the data and typically lives on its own separate database server.
So you might put users AM on one server and NZ on another.
That's the basic idea, yes. You need to choose a shard key, some piece of data, like the first letter of the username or maybe the user ID modulo some number, that determine which shard a particular piece of data belongs to.
Choosing that key seems important.
It's critical. A bad shard key can lead to hotspots where one shard gets way more traffic than others, defeating the purpose of distributing the load. Planning your sharding strategy carefully is crucial for large-scale relational databases.
Okay, so replicas for reads, sharding for massive data size. These distributed systems sound complex with lots of moving parts. What happens when things inevitably go wrong, like network issues between servers?
That brings us to a really fundamental, almost philosophical concept in distributed systems, the CAP theorem.
CAP theorem? Heard of it? Sounds important. CAP.
Exactly. It was proposed by Eric Brewer. It states that any distributed data store can only provide two out of the following three guarantees simultaneously. Consistency. Every read receives the most recent write or an error. All nodes see the same data at the same time. Availability. Every request receives a non-error response without guaranteeing it contains the most recent write. The system is always up to respond. Partition tolerance. The system continues to operate despite an arbitrary number of messages being dropped or delayed by the network between nodes. It keeps working even if parts of the system can't talk to each other.
Okay, consistency, availability, partition tolerance. Pick two.
In reality, for most distributed systems operating over the internet, network partitions will happen. So partition tolerance, P, is usually something you have to deal with.
Right, the network isn't perfectly reliable.
So the real trade-off forced by the CAP theorem is usually between consistency C and availability A when a partition occurs.
Choose C or A when P happens.
Exactly. Do you want the system to potentially return stale data but always be available, choosing A over C? Or do you want it to guarantee consistent data, even if that means returning an error or becoming unavailable if it can't ensure consistency during a partition, choosing C over A?
Wow, that forces some hard decisions.
It really does, and it explains why different systems make different choices. Your bank prioritizes consistency, CP systems. A social media feed might prioritize availability, AP systems, accepting eventual consistency. Understanding CAP is crucial for designing and reasoning about any distributed system.
That clarifies so much about the trade-offs involved. Okay, let's start weaving these threads together. How do architects use these concepts, scaling, load balancing, caching, databases, CAP choices, to build really complex real-world apps? So we get into designing at scale, right?
Absolutely. And a key theme here is moving towards asynchronous communication and decoupling.
Asynchronous.
Okay.
Meaning not waiting for an immediate response.
Exactly. Instead of Service A directly calling Service B and waiting for it to finish, Service A can put a message onto a message queue.
Like a digital mailbox.
Sort of, yeah. Think systems like RabbitMQ or AWS SQS. Service A drops a job request message into the queue and can immediately move on to other tasks. Later, Service B, or multiple instances of Service B, can pick up that message from the queue and process it at its own pace.
Ah, so they don't have to be available at the exact same moment.
Right. This decouples the services. If Service B is temporarily down or overloaded, the messages just pile up in the queue, waiting to be processed when it recovers. It improves reliability and scalability, as you can scale the number of message producers and consumers independently.
That sounds really useful. What about broadcasting messages? Like one event happens and multiple different services need to know about it.
That's a perfect use case for the publish-subscribe pattern, often called PubSub.
PubSub.
Systems like Apache Kafka or Google PubSub excel at this. A service, the publisher, sends a message to a topic. Other services, subscribers, can subscribe to that topic. When a message is published to the topic, all the subscribers receive a copy.
So one message, many listeners. Like sending out a newsletter.
Good analogy. It's great for things like event notifications, real-time data pipelines, fanning out work to different types of processors. Again, it decouples the publisher from the subscribers.
Okay, message queues for one-to-one decoupling, PubSub for one-to-many. This sounds like it enables breaking down big applications.
It absolutely does. It's a key enabler for architectures like service-oriented architecture, SOA, and its more modern, fine-grained evolution, microservices.
Microservices, everyone talks about those, breaking the monolith.
Right. Instead of having one massive application, a monolith that does everything, you break it down into many small independent services, each responsible for a specific business capability. Maybe one service handles user authentication, another handles the product catalog, another handles payments.
Each potentially using its own database, its own scaling strategy.
Exactly. They communicate typically over the network using APIs, often asynchronously via queues or PubSub. This allows teams to develop, deploy, and scale services independently.
Sounds great, but how do all these tiny services find each other? If the payment service needs to talk to the user service, how does it know its address, especially if new instances are constantly popping up and down due to scaling?
That's the challenge of service discovery.
Right.
You need a mechanism like a registry 4G console, etc., or cloud provider services, where services can register themselves when they start up. Here I am, I handle payments at this address. And where other services can query to find the current healthy instances of the services they need to talk to. It's like an internal DNS for your microservices.
Got it. Essential plumbing for that architecture.
Hmm.
Beyond the big architectural patterns, are there specific algorithms or techniques that pop up frequently in advanced designs?
Definitely. A couple key ones come to mind. First, rate limiting.
Limiting how often someone can do something.
Precisely. It's crucial for protecting your APIs and backend services from abuse, whether intentional, like a DDoS attack, or unintentional, like a buggy script sending too many requests. You set limits, like a user can only make 10 requests per second to this API and enforce them, usually at the gateway or load balancer level.
Protects the system, ensures fair usage. Makes sense. What else?
Another really clever technique, especially relevant for distributed caching and load balancing across many servers, is consistent hashing.
Consistent hashing. Sounds mathematical.
It is a bit, but the concept is powerful. Imagine you have data spread across 10 cache servers. If you add an 11th server, traditional hashing might require moving almost all the data around to rebalance. Consistent hashing is a technique that minimizes this disruption. When a server is added or removed, only a small fraction of the keys, data items, or requests need to be remapped.
So it makes adding or removing servers much less painful and disruptive.
Exactly. It's widely used in systems like Amazon's DynamoDB, CDNs, and load balancers to distribute load or data smoothly across a dynamic set of nodes.
Okay, wow. We've covered a ton, from the basics up to these advanced techniques. How do these actually play out in designing familiar things? You mentioned URL shorteners or social feeds.
Right. Let's connect it back. Think about designing a URL shortener like TinyURL. You need a way to generate short keys, store the mapping between the short key and the long URL, maybe a NoSQL key value store for scalability, handle redirects incredibly quickly, caching is key, and deal with potentially billions of entries.
Okay, I can see the pieces fitting. What about a social media feed like Twitter or Instagram?
Immensely complex. You have massive write volume, people posting constantly, massive read volume, people scrolling feeds. How do you generate personalized feeds for millions of users efficiently? Probably involves read replicas, extensive caching, maybe PubSub for distributing new posts, NoSQL for storing posts, and thinking hard about consistency versus availability.
Right, that eventual consistency probably plays a big role there.
Absolutely. Or a ride-sharing app like Uber or Lyft. Matching riders and drivers in real time involves geospatial indexing, real-time messaging, maybe WebSockets or MQTT, handling payments securely, calculating surge pricing.
Wow, or even just search autocomplete.
Yeah. As you type, it needs to suggest relevant queries almost instantly. This might involve specialized data structures like tries, pre-computed results, heavy caching, and techniques to handle high query volume efficiently. Each of these problems requires combining the building blocks we've discussed in clever ways, always focusing on the specific requirements and trade-offs.
It really shows how these concepts are the Lego bricks for building the entire digital world.
That's a great way to think about it.
Now, for folks who really want to go deep, or maybe even work in this field, what are some of the more expert-level nuances that signal a really deep understanding?
Good question. Beyond the core concepts, diving into the subtleties is key. For example, really understanding the different consistency models. We talked about strong versus eventual, but there's a whole spectrum in between, like causal consistency or read your rights consistency. Knowing when each is appropriate is advanced stuff.
Okay, a deeper dive on consistency. What else?
Understanding leader election algorithms. In many distributed systems, you need one node to be the leader responsible for coordinating actions or managing rights. How is that leader chosen reliably, especially if the current leader fails? Algorithms like Paxos or Raft solve this, and while complex, knowing the principles is important.
Choosing the boss, basically.
Chuckles. In a distributed, fault-tolerant way, yes. And then, absolutely critical at an expert level is monitoring and observability.
Seeing what's actually happening inside the system.
Exactly. You often hear about the 3 pillars: metrics, time series numerical data, CPU usage, request latency, error rates, cache hit rates, things you can plot on graphs, logging, detailed, time-stamped records of specific events happening within services, user X logged in, database query failed, etc. Tracing, following the path of a single request as it travels through multiple microservices showing timing and dependencies.
Metrics, logging, tracing, the 3 pillars.
Without robust systems for all 3, you're essentially flying blind when trying to understand performance issues, debug problems, or even just know if your system is healthy. Observability is non-negotiable for complex systems.
That makes perfect sense. You can't fix what you can't see. Now, this all sounds incredibly complex. If someone, say, in an interview, or even just tackling a big design problem, how do they approach it systematically? Is there a framework?
Yes, absolutely. The standard system design interview framework is actually a really good mental model for tackling any complex system problem. It provides structure.
Okay, what are the steps?
It usually goes something like this. 1, clarify requirements. Really dig in. What are the functional requirements? What should it do? And crucially, the non-functional requirements. How well should it do it? Things like expected requests per second, data size, required latency, availability targets like 99.99% uptime.
Understand the goals and constraints first.
Absolutely. Then 2, back of the envelope estimation. Do some quick calculations. Estimate traffic, storage needs, bandwidth. This helps justify your design choices later. We expect 1 billion requests per day, so we need X servers.
Sanity check the scale.
Right. 3, high-level design. Sketch out the main components, draw a block diagram showing the major services, databases, caches, load balancers, etc., and how they connect.
The big picture.
4, deep dive. This is the core. Zoom in on specific components. Justify your choices. SQL versus NoSQL, which caching strategy, REST versus GraphQL. Discuss potential bottlenecks. How would you scale this component? What are the trade-offs you made?
Getting into the details and rationale.
And finally, 5, summarize and refine. Briefly recap your design. Discuss potential future improvements, edge cases, monitoring strategies, or how you'd handle specific failure scenarios.
It provides a logical flow for breaking down a massive problem.
Exactly. It turns a daunting task into a structured conversation about trade-offs and solutions.
Wow. Okay, what an incredible journey we've been on. From the moment you type that web address
That DNS lookup.
to the TCP handshake, the HTTP request, the server processing, maybe talking to other services via APIs,
Hitting databases, using caches.
all orchestrated across potentially thousands of machines, balanced, monitored. It's just staggering. We've really peeled back the layers on system design today.
And hopefully that's the real takeaway. It's not just about knowing the terms, but appreciating the immense hidden complexity, but also the ingenuity behind the technology we use every single day without a second thought.
Yeah, it definitely gives you a new perspective.
It lets you see the digital world with, well, slightly different eyes, perhaps.
Absolutely. So here's a final thought for you listening. Now that you understand just how much complexity and interconnectedness it takes to make even a simple Google search work, what other everyday digital interactions do you think hold surprising layers of system design just beneath the surface?
Sending an email, paying with your phone, streaming a movie.
Exactly. There's depth everywhere. We really hope this deep dive has sparked your curiosity to keep exploring. Thanks so much for joining us today.
Yeah, thanks for listening.